Good morning, good afternoon, and good evening, everyone. I'm going to talk about geothermal energy and its potential. This is a hodgepodge of information that I've gathered from all the resources that I've looked at from the internet, and I decided to compile it in a presentation. The inspiration behind this presentation is when I gave a talk on geothermal energy and its potential in India for a student's chapter in SPE. As usual, please be sure to like this video, subscribe so you can get more content in oil and gas and professional development topics, and please be sure to comment on the video below on the YouTube platform so I can incorporate your feedback into future videos. Now let's get to the presentation. I wanted to start off pretty easy. What exactly is geothermal energy? It is heat within the earth. The word comes from Greek words such as geo and therm. Geothermal energy is a renewable energy source because heat is continuously produced inside the earth. People use geothermal heat for bathing, to heat buildings, and to generate electricity. This comes straight from the EIA. Here are the benefits of geothermal energy, and this comes straight from the Department of Energy in the United States. It's renewable, the base load, there's a domestic benefit, there's a small footprint, and it's clean. For renewable, through proper reservoir management, the rate of energy extraction can be balanced with the reservoir's natural heat and recharge rate. Geothermal power plants produce electricity consistently, running 24 hours a day, 7 days a week, regardless of weather conditions. U.S. geothermal resources can be harnessed for power production without importing fuel. Geothermal power plants are compact, using less land per gigawatt hour than coal, wind, and solar with center station. In modern closed-loop geothermal power plants emit no greenhouse gases. Life cycle greenhouse gas emissions are 4 times less than solar and 6 to 20 times lower than natural gas. Geothermal power plants consume less water on average over the lifetime energy output than most conventional generation technologies. Here are the general challenges of geothermal energy. One concern of geothermal power is its use of groundwater. The process of extracting this water may unintentionally release carbon dioxide and hydrogen sulfide into the atmosphere. Mitigating the release of these emissions is a key challenge with developing this technology. The costs of geothermal energy are largely incurred upfront. Simply put, it is expensive to carry out the seismic sensing, test well drilling, confirmation testing, and other necessary preliminary investigations to ensure that a geothermal plant will be capable of meeting desired product specs. So how does a geothermal power plant work? These power plants use steam to produce electricity. The steam comes from reservoirs of hot water found a few miles or more below the Earth's surface. The steam rotates a turbine that activates a generator, which produces electricity. There are 3 types of geothermal power plants: dry steam, flash steam, and a binary cycle. I'll first talk about the dry steam. They draw from underground resources of steam. Steam is piped directly from underground wells to the power plant, where it is directed into a turbine generator unit. There are only 2 known underground resources of steam in the U.S., the geysers in Northern California, and then Yellowstone National Park in Wyoming, where there is a well-known geyser called Old Faithful. Since Yellowstone is protected from development, the only dry steam plants in the country are the geysers. Now I'll talk about flash steam. These are power plants that are most common and use geothermal reservoirs of water with temperatures greater than 360 degrees Fahrenheit or 182 degrees centigrade. The very hot water flows up through wells in the ground under its own pressure. As it flows upward, the pressure decreases and some of the hot water boils into steam. The steam is then separated from the water and used to power a turbine or generator, and any leftover water and condensed steam are injected back into the reservoir, making this a sustainable resource. Binary steam. Binary cycle steam power plants operate on water at lower temperatures at 225 to 360 degrees Fahrenheit or 107 to 182 degrees Celsius. The binary cycle plants use the heat from the hot water to boil a working fluid, usually an organic compound with a low boiling point. The working fluid is vaporized in a heat exchanger and used to turn a turbine. The water is then injected back into the ground to be reheated. The water and the working fluid are kept separated during the whole process, so there are little or no air emissions. Currently, two types of geothermal resources can be used in binary cycle power plants to generate electricity: enhanced geothermal systems, or EGS, and low temperature or co-produced resources. I'll talk about EGS. It provides geothermal power by tapping into the Earth's deep geothermal resources that are otherwise not economical due to lack of water, location, or rock type. The U.S. Geological Survey estimates that potentially 500,000 megawatts of EGS resources available in the western U.S., or about half of the current installed electric power generating capacity in the U.S. Now I'll talk about low temperature and co-produced resources. They're typically found at temperatures at 300 degrees Fahrenheit or 150 C or less. Some low temperature resources can be harnessed to generate electricity using the binary cycle technology. Co-produced hot water is a byproduct of oil and gas wells in the United States. This hot water is being examined for its potential to produce electricity, helping to lower greenhouse gas emissions and extend the life of oil and gas fields. I got this straight from the EPA of how it works of the power plants. So if you look at the bottom right, the hot water is pumped from a deep underground through a well under high pressure. When the water reaches the surface, the pressure is dropped, which causes the water to turn into steam. The steam spins a turbine, which is connected to a generator that produces electricity. The steam cools off in a cooling tower and condenses back to water. The cooled water is pumped back into the earth to begin the process again. Now here's how a geothermal heat pump works. Water or refrigerant moves through a loop of pipes. When the weather is cold, the water or refrigerant heats up as it travels through the part of the loop that is buried underground. Once it gets back above ground, the warm water or refrigerant transfers heat into the building. The water or refrigerant cools down after its heat is transferred. It is pumped back underground where it heats up once more, starting the process again. On a hot day, the system can run in reverse. The water or refrigerant cools the building and then is pumped underground where extra heat is transferred to the ground around the pipes. I wanted to show this as an overview of geothermal projects that are worldwide, just to give a scope of what we're talking about when we're referring to geothermal energy and the extent of this type of energy to affect different parts of the world. Now I'll talk about geothermal drilling. It covers a wide range of activity from shallow to very deep. The shallow wells use radiated heat from the sun, held in the formation, commonly referred to as ground source heat, whereas deep wells use elevated temperatures that are a result of various geological activities that include volcanic or magmatic systems, heating of igneous rocks from the Earth's core, and hydrothermal systems, where fluids are heated at depth. Depending on the resource temperature, the heat is used to produce electricity, heat, and where is possible combination of the two. Depothermal geothermal wells adopt drilling techniques used in oil and gas, although they are not best suited to the types of formations encountered in geothermal fields and could lead to high well costs, relative to the price that geothermal energy can be sold for. As geothermal energy usage increases, there will be an exponential increase in industry-specific equipment. We are already seeing oil and gas drilling equipment manufacturers moving into the sector, although equipment is often just tweaked and costs remain high. While many geothermal areas are similar in nature to oil and gas areas, the subtle differences required for a successful well can all too easily be missed. The main areas for consideration or concern are where the geology is wholly different to those normally encountered or avoided in oil and gas wells, namely igneous and metamorphic rocks, although shale is now heavily being exploited for gas, where formations have high strengths, highly abrasion, heavily faulted, folded, and often zones where fluids can disappear, never to be seen again. While oil and gas wells present the risk from highly combustible gases being present in the formations, geothermal wells also have a high risk potential from very hot fluids at very high pressures that, when drilled into, turns instantly into steam, which are difficult to contain or control. Just imagine heating a tinned fruit in sugary water in your oven at 2500 Celsius for a couple of hours, taking it out and piercing a hole on the top. So this directly comes from GeoDrill project at EU. Now here are the costs to drill geothermal wells. They can vary in depth, but for a larger scale energy usage, they're usually drilling depths between 3 to 5 kilometers, although wells are becoming deeper. Well drilling costs can also vary greatly depending on the formation type, the type of well drilled, depth drilled, and the nature of the resource encountered. It is difficult to accurately predict the cost of a geothermal well, but currently a figure between £2,200 and £2,500 per meter drilled and completed for the exploitation of geothermal energy is a reasonable estimate. Compare this to a shale gas well with a complex drilling geometry that is around £900 per meter drilled. But this can vary. Now I'll talk about geothermal reservoir engineering. It has its roots in petroleum reservoir engineering and historically relies on conventional petroleum methods with slight modifications to account for inherent differences in conditions. It was not until the late 1960s and early 1970s that engineers recognized that they must include a rigorous energy balance to account for the interface mass and energy exchange and other heat transfer mechanisms that arise from vaporization of fluid during extraction operations. Now I'll talk about the differences between petroleum and geothermal reservoir engineering. The reservoir fluid has no inherent value in and of itself. The fluid can be viewed as a working fluid whose sole value is the energy it contains. Geothermal reservoirs in the native state are rarely static and are usually neither isothermal nor of uniform fluid composition. Large spatial variations in pH occur. Highly corrosive reservoir fluids are not uncommon and lead to additional expense of drilling, completions, and production. Geothermal reservoirs are rarely completely closed. More often, a zone of recharge and multiple zones of discharge, including springs and fumaroles, are associated with the resource. Phase behavior is deceptively complex. In its simplest form, the reservoir fluid as a single component may partition up to 3 phases: liquid, vapor, and absorbed phases. Usually there are additional components such as non-condensable gases and salts. Geothermal reservoirs are typically found in highly fractured or igneous metamorphic rocks. Very few are found in said rocks worldwide. While rock matrix properties would make the resource commercially unattractive as a petroleum reservoir, the relatively large dimensions ensure a substantial resource or heat is in place. This comes directly from PetroWiki as far as the differences between petroleum and geothermal reservoir engineering. I want to talk a little bit about the Utah Forge project, which is a large geothermal project that is in the United States. It's a dedicated and underground field lab sponsored by the Department of Energy for developing, testing, and accelerating breakthroughs in enhanced geothermal systems, technologies to advance the uptake of geothermal resources around the world. It is located near the town of Milford in Beaver County, Utah, on the western flank of the Mineral Mountains. Near-term goals are aimed at perfecting drilling, stimulation, injection production, and subsurface imaging technologies required to establish and sustain continuous fluid flow and energy transfer from an EGS reservoir. The mission is to enable cutting-edge research in drilling and technology testing, as well as to allow scientists to identify a replicable commercial pathway to EGS. In addition to the site itself, the Forge effort will include a robust instrumentation, data collection, and data dissemination component to capture and share data and activities occurring at the Forge at real time. The innovative research coupled with an equally innovative collaboration and management platform is truly a first kind of endeavor. This ends up providing an underground lab for developing and testing innovative tools and stimulation techniques for developing EGS reservoirs, extend the existing technologies developed for oil and gas beyond current capabilities to successfully produce electricity from hot crystalline rocks, demonstrate technologies that can be applied across the USA, provide domestic and international scientists and students with funds for research to expand future energy security and availability, demonstrate the suitability and safety of large-scale geothermal energy development to the public. You can get more information at utahforge.com. I want to talk about a few case studies from some papers that have discussed geothermal energy from different countries. This is one in Finland. The title of the paper is called Technologies and Environmental Impacts of Ground Heat Exchangers in Finland. Cold climate and crystalline bedrock define GSHP or ground source heat pumps operating conditions in Finland. Borehole heat exchanger is the most popular collector type in Finland. Most common complications are collapsed boreholes and artesian or high water yield. Fluid leakages connecting multiple aquifers and design errors are also discussed. The next case study I want to talk about is in Chile. Understanding the social acceptance of geothermal energy, which is a case study from the Araucanía region in Chile. The general attitudes during geothermal energy in Chile are discussed. The Villarrica community was characterized by low level of understanding of geothermal energy production. There is a lack of trust, spiritual relationship to volcanoes, and uncertainty about environmental impact affecting public perception of geothermal energy. And direct uses of geothermal energy appear to be a great opportunity to introduce this renewable energy. The last case study I wanted to talk about is in India, which is the hydrochemistry, geothermometry, and the origin of low-temperature thermal springs in South Konkan region in India. Geochemical and isotropic composition of 2 low-temperature thermal springs in the South Konkan region, South India, were studied. These thermal waters are of NaHCO3 type peripheral waters. Geochemical classification indicate the dissolution of silicate minerals controls chemical composition of this thermal water system. Stable isotope composition indicate meteoric origin of thermal waters without the isotope exchange by interaction with host rocks. And the results suggest that these thermal springs are most likely part of a fault-controlled shallow hydrothermal system. The next one is the geophysical exploration of the Thural Rajwadi group of hot springs, west coast of Maharashtra, and its implications. The Thural Rajwadi hot springs from the west coast India yield a low discharge of 50 to 61 degrees Celsius. They occur within the Deccan Trap basalt and have a high geothermal gradient. Isothermal fluid flow in borehole indicates heat transfer by hydrothermal convection. Geophysical studies identify prominent north-northwest, south-southeast, northeast-southwest, and northwest-southeast lineaments and subvertical conduit system for geothermal utilization. And 2D gravity modeling and depth analysis techniques show granitic basement at 770 to 800 meters below ground level. That is the end of the presentation. Here are some other resources of geothermal energy that I've listed below. Feel free to reach out to me or direct message me, find me on LinkedIn or on Facebook so I could provide these slides to you and you can share them with other folks. As usual, please be sure to like this video, subscribe so you can get more content in oil and gas and professional development topics, and please be sure to comment on the video on the YouTube platform so I can incorporate your feedback into future videos. Thank you so much for taking the time to watch this video, and I'll see you in the next one.